There is one question that human beings have been asking for, as long as we have been able to look up at the night sky and wonder, are we alone? For most of human history, that question lived in the territory of philosophy, religion, and imagination. We had no way to answer it scientifically. We could speculate, we could hope, we could fear, but we could not test. That era is now over. For the first time in the history of our species, we have built instruments sensitive enough, powerful enough, and clever enough to actually go looking for life on other worlds. We have rovers drilling into ancient lake beds on Mars. We have spacecraft flying through geysers erupting from the ocean floors of distant moons. We have a space telescope reading the chemical composition of atmospheres around planets orbiting other stars. The search for life beyond Earth has moved from science fiction into hard science, and what we are finding is simultaneously thrilling, puzzling, and deeply humbling. This video is the story of that search, where we are looking, what we have found so far, what the next generation of missions is designed to discover, and what it would mean for humanity if the answer turns out to be yes, or if it turns out to be no. Both answers would change everything. But before we can go looking for life, we need to be honest about something that makes this search genuinely difficult. We do not have a universally agreed upon definition of what life actually is. That might sound surprising, but it is true, and it matters enormously for how we design our search. The definition most widely used in astrobiology comes from Gerald Joyce. In 1994, he described life as a self-sustaining chemical system capable of Darwinian evolution. That captures the two things that seem most essential. First, they maintain themselves through continuous chemical activity. Second, they can pass on heritable information to offspring. But Stephen Benner pointed out in 2010 that this definition carries hidden assumptions rooted entirely in Earth life. It might exclude viruses or miss alien forms of chemistry. Benner argues we should treat definitions as guides rather than rigid gates, keeping our minds and our instruments open to the unexpected. So, while the precise definition remains debated, science has converged on 5 practical requirements that any life as we understand it needs in order to survive. The first requirement is liquid water. Water is an almost miraculous solvent. Its molecular structure gives it a strong electrical polarity. This means it can dissolve an enormous range of salts and organic molecules and bring them into close enough contact to react at biological speeds. Water also has an unusually high capacity to absorb and store heat, which buffers living systems against the temperature swings of day and night. And water does something strange and beautiful when it freezes. Unlike almost every other liquid, water expands rather than contracting, which means ice floats. This allows entire ecosystems to survive underneath a frozen lid. This property is why vast liquid water oceans can exist beneath the icy shells of moons like Europa and Enceladus. Other solvents have been proposed, like liquid ammonia or methane, but every living organism we have ever found requires liquid water. The second requirement is carbon. Carbon is the structural backbone of all known life because of a remarkable bonding versatility that no other element matches. Each carbon atom can form 4 strong, stable bonds, producing branched chains, rings, and spirals of almost limitless variety. This diversity is what allows life to build. Silicon is sometimes proposed, but it forms weaker bonds, and its oxide is a solid mineral, which prevents the atmospheric cycling that life needs. The third requirement is energy. Life cannot exist in thermodynamic equilibrium. It continuously consumes energy to maintain its internal organization. On Earth, the dominant source is sunlight, but chemosynthesis powers entire ecosystems in places sunlight never reaches, like deep rock communities kilometers underground. The fourth requirement is the set of 6 elements that all known life is built from: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, CHNOPS. The fifth requirement is thermodynamic disequilibrium. Life needs chemical gradients to exploit. A universe in perfect balance has no free energy for life to harvest. Now, here is one of the most important developments. Extremophiles are organisms that thrive in conditions once considered completely uninhabitable. Giagemma barosi grows and reproduces at 121 degrees Celsius, hotter than boiling water at sea level. At the opposite extreme, Planococcus halocriophilis remains active at -15 degrees Celsius in the Arctic permafrost. Picrophilus torridus thrives in acid stronger than battery acid, while Deinococcus radiodurans survives radiation doses that would kill a human 1,000 times over. Entire microbial communities live inside the pores of rocks several kilometers underground, surviving entirely on chemical energy. Studies suggest the total microbial biomass in Earth's subsurface may account for roughly 70% of all microbial life on the planet. If 70% of Earth's life lives underground in the dark, then the idea of a subsurface ocean on Europa hosting life becomes far less exotic and far more plausible. In 1953, Stanley Miller and Harold Urey passed electrical sparks through a mixture of gases. Within a week, the flask contained amino acids. The chemistry of life could assemble itself. Walter Gilbert proposed that RNA may have been the first self-replicating molecule, an idea called the RNA world hypothesis. Michael Russell and William Martin have championed the idea that alkaline hydrothermal vents on the early ocean floor gave rise to protocells. Even the building blocks of life appear to arrive from space. The Murchison meteorite was found to contain more than 90 different amino acids. Glycine was detected in samples returned from Comet Wild 2. The organic chemistry of life is clearly not confined to Earth. It is a natural product of the cosmos. Of all the places beyond Earth, Mars holds a uniquely compelling position. It is the closest planet to us that once had conditions genuinely compatible with life. Orbital spacecraft have photographed ancient valley networks carved into the Martian surface that look almost identical to river drainage systems on Earth. Hematite spherules, nicknamed blueberries, were found by the Opportunity rover. They form in ancient water-rich environments where minerals precipitate out of liquid. Mars experienced genuinely habitable surface conditions during a period roughly 4 billion years ago, known as the Noachian era. Early Mars was wetter and warmer. The most intriguing and maddeningly unresolved mystery involves methane. On Earth, 95% of methane comes from biological sources. When the Curiosity rover measured trace gases, it detected methane. Not a lot, but its presence is significant because methane is destroyed quickly by radiation. Something must be actively replenishing it. The sources could be biological or completely abiotic chemical reactions. Both are scientifically plausible. The puzzle deepened when the Trace Gas Orbiter detected essentially no methane at all from orbit. How can a rover on the ground detect what an orbiter cannot? The answer remains unknown. Perhaps methane is released locally and destroyed before it can mix upward. It's like a smoke alarm with no visible fire. Into this environment, NASA landed the Perseverance rover in Jezero Crater in 2021. Jezero is an ancient impact basin that was once a lake. A river once flowed into Jezero, depositing a fan-shaped delta. Deltas on Earth are among the best environments for preserving biological material. Perseverance carries instruments like Sherlock and Pixel to hunt for biosignatures at the chemical level, looking for patterns that biological activity leaves behind. In 2025, scientists described mudstones containing nodules enriched in iron and sulfur. On Earth, this combination is exactly what ancient microbial communities leave behind. These are genuine potential biosignatures, but the rover cannot definitively distinguish them from abiotic chemistry. This is why it is collecting samples in titanium tubes. Mars sample return is the highest priority. Only the massive instruments in laboratories on Earth can definitively determine if these are the remains of Martian life. Present-day Mars is hostile. The atmosphere is thin, radiation is high, and the soil is filled with toxic perchlorate. Surface life seems essentially impossible. But below the surface, the radiation is manageable, and liquid water may persist. The Rosalind Franklin rover, launching in 2028, will drill deep to find what clings to survival. One of the most profound shifts in astrobiology over the past 2 decades has been the realization that the search for life does not have to be confined to the narrow band around a star where surface liquid water can exist. Tidal heating, the gravitational kneading of a moon by the combined pull of its host planet and neighboring moons, can keep an ocean liquid for billions of years, even in the frozen outer solar system, hundreds of millions of kilometers from the sun. 3 moons in the outer solar system have emerged as the most compelling ocean world targets, each remarkable in its own way. Europa, one of Jupiter's 4 large moons, is slightly smaller than Earth's own moon, with a diameter of about 3,100 kilometers. Beneath its smooth, cracked, icy surface lies a global saltwater ocean estimated to contain roughly twice the total volume of all of Earth's oceans combined. The ocean is kept liquid by tidal heating, generated by the gravitational resonance between Europa, its neighbor Io, and the massive pull of Jupiter itself. The surface temperature averages around -163 degrees Celsius, cold enough to keep the outer ice shell frozen solid. But the ocean beneath may be kept at temperatures that allow water to remain liquid indefinitely. The existence of this hidden ocean was demonstrated not by drilling through the ice, but through a beautiful piece of physics. The Galileo spacecraft carried a magnetometer that detected a magnetic signature from Europa that could only be explained by a conducting layer beneath the surface. Specifically, a layer of saltwater ocean generating an induced magnetic field in response to Jupiter's powerful magnetosphere. Margaret Kyvelson at UCLA and her colleagues published this definitive result in the journal Science in 2000. More recently, the Juno spacecraft flying close to Europa used microwave instruments to constrain the thickness of the ice shell to roughly 29 kilometers. Meaning the ocean beneath is separated from space by a layer of ice about as thick as the distance across a major city, but covering an entire planetary surface. Hubble Space Telescope observations have intermittently detected what appear to be water vapor plumes erupting from Europa's south polar region. Danso arrestors dar refor dar enso answers. Reported by Lawrence Roth and colleagues in Science in 2014. If these plumes are real and recurring, they would represent an extraordinary opportunity. Material from Europa's ocean, potentially including any chemistry or biology it contains, would be venting directly into space, where a spacecraft could fly through and sample it without needing to land or drill. This possibility is a central motivation behind NASA's Europa Clipper mission, launched on October 14, 2024. Europa Clipper carries 9 specialized instruments, including an ice-penetrating radar to sound through the ice shell, a mass spectrometer to analyze any plume gases the spacecraft encounters, a dust analyzer to examine ejected ice particles, a near-infrared spectrometer to map surface chemistry, and a magnetometer to precisely characterize the ocean's properties through its electromagnetic signature. The spacecraft will conduct 44 close flybys of Europa at altitudes ranging from 25 to 2,700 kilometers after arriving at Jupiter in April 2030. Europa Clipper will not directly detect life. What it will do is determine definitively whether Europa's ocean has the ingredients and conditions that life as we understand it would require. Kevin Hand at NASA's Jet Propulsion Laboratory has articulated the stakes clearly, noting that finding life in Europa's ocean would demonstrate that life is not a rare cosmic accident, but a natural outcome whenever conditions permit. Now let us talk about a moon that is in some ways even more immediately accessible than Europa. Enceladus is one of Saturn's moons, small enough to fit inside the borders of metropolitan France with a diameter of only 504 kilometers. It is the most reflective object in the solar system because its surface is coated in fresh, white water ice, giving it a geometric albedo of 0.99. Meaning it reflects essentially all the light that hits it. In 2005, the Cassini spacecraft, flying close to Enceladus, discovered something extraordinary. From 4 long cracks near the moon's south pole, nicknamed tiger stripes, enormous plumes of water vapor and ice crystals were erupting continuously into space, creating a vast cloud of material that feeds one of Saturn's faint outer rings. Carolyn Porco and her colleagues reported this discovery in Science in 2006. What Cassini found in those plumes over the following decade of observations was staggering in its astrobiological implications. Frank Postberg and colleagues showed in 2009 that the plume particles contain salt-rich ice grains, indicating that the plumes are drawing directly from a global subsurface ocean. Jezero Crater Bardi Kier Aris Guris Darby Seri Dari Seri Serix. in contact with a rocky core, not just from melting surface ice. In 2015, Xiang Wen-Shu and colleagues detected tiny silica nanoparticles in Saturn's E-ring that could only have formed through hydrothermal activity at temperatures above 90 degrees Celsius, implying that hot water is circulating through the rocky seafloor. In 2017, Jack Waite at the Southwest Research Institute and his colleagues detected molecular hydrogen in the plumes using Cassini's mass spectrometer. Molecular hydrogen is produced when hot water reacts with certain types of rock in a process called serpentinization. On Earth, this same chemical reaction at hydrothermal vents is exploited by microorganisms called methanogens as their energy source. Carolyn Porco summarized the cumulative findings by noting that Enceladus has all the ingredients of a habitat for life, including liquid water, organics, chemical energy, salts, and nitrogen-bearing compounds. The final piece of the habitability puzzle fell into place in 2023 when Frank Postberg and his team announced the detection of sodium phosphates in Enceladus plume particles. Axaris dan the Dakari Oxakinstier Nander Ashensandi. At concentrations 100 to 1,000 times higher than in Earth's oceans. Phosphorus is the P in CHNOPS, the rarest of the 6 elements essential for all known life. And its detection in the plumes completed the full chemical inventory required for Earth-style biochemistry: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The plumes of Enceladus are like a free sample of the ocean being handed directly to any spacecraft willing to fly through them. We do not need to land, we do not need to drill, we just need to catch the spray. Naturally, Enceladus has been ranked as the highest priority flagship mission target in the 2023 Planetary Science and Astrobiology Decadal Survey. The proposed Enceladus Orbilander would first orbit the Moon to characterize the plumes in detail and then land near a tiger stripe fracture to sample material directly. Estimated at roughly $2.56 billion, the mission has not yet been funded. The third ocean world deserves mention because it is genuinely unlike anything else in the solar system. Titan, Saturn's largest moon, Badurur, Daberber, Daberbo, Acherbur, Anderkuri, Mandurbani, Nasamnukuri, Isambukuri, Masur, Iseruri, Isanukuri, is bigger than the planet Mercury and is the only moon in the solar system with a thick atmosphere. At its surface, the atmospheric pressure is about 1.5 times Earth's sea level pressure. So you could walk around on Titan's surface without a pressure suit, though you would need insulation because the surface temperature averages minus 179 degrees Celsius. The atmosphere is mostly nitrogen, with a small percentage of methane, and complex photochemistry converts these gases into organic molecules called tholins that rain down onto the surface. Titan's surface is covered with lakes and seas, but they are not water. They are liquid methane and ethane, making Titan the only body with stable surface liquid other than Earth. Could life exist in liquid methane rather than liquid water? Researchers have explored whether cell-like structures called azotosomes could form using nitrogen-rich organic molecules. These ideas remain highly speculative, but Titan also possesses a subsurface liquid water ocean beneath its ice shell, according to gravity data from Cassini. NASA's Dragonfly mission is designed to explore Titan's surface directly. It is a nuclear-powered rotorcraft lander, essentially a large drone. Associaturus before understatement so desto that will fly through Titan's thick atmosphere from site to site over the course of more than 3 years after landing, scheduled for launch in July 2028. Dragonfly will explore both ancient dune fields and an impact crater called Selk, where the heat of impact may have briefly melted water ice and mixed it with surface organics. Nanar Rebisher, Danacrosaparir, Danafrositabrier, Denshurder, creating a transient warm water environment where prebiotic chemistry might have occurred, searching for the molecular building blocks of life. Everything we have discussed so far involves worlds we can reach with robotic spacecraft, worlds within our own solar system that we can study up close. But the solar system contains only one confirmed example of life, and that is us. To understand whether life is common, we need to look at other solar systems. For most of human history, this was completely impossible. We could not even detect planets around other stars, let alone study their atmospheric chemistry. That has changed. The instrument that changed it most dramatically is the James Webb Space Telescope. When a planet passes in front of its star, a tiny fraction of starlight filters through its atmosphere. Different molecules absorb light at specific wavelengths, leaving characteristic dips in the transmitted spectrum, like a chemical fingerprint. The technique is called transit spectroscopy. It is about as delicate a measurement as any in modern science. One scientist described it as like standing a mile from a lighthouse and trying to determine the composition of a gnat's wings. The gases that would most compellingly indicate life are combinations of molecules that should not coexist without biological activity, like oxygen and methane together. Life on a planet would drive its atmosphere into a state of chemical disequilibrium. This idea was first articulated by James Lovelock in the 1960s. Joshua Chrysanson Totten and colleagues quantified this in 2018, showing that Earth's disequilibrium is orders of magnitude greater than any purely abiotic planet model. Ozone, nitrous oxide, and dimethyl sulfide have been proposed as biosignatures. DMS is particularly compelling as it is produced almost exclusively by marine phytoplankton. In 2023, JWST observed a planet called K2-18b, sitting within the habitable zone of its star 124 light-years away. The data revealed carbon dioxide and methane. A hint of dimethyl sulfide was detected, sparking debate. Subsequent reanalysis found no conclusive evidence, showing that claims of biosignatures require extraordinary scrutiny. The TRAPPIST-1 system offers perhaps the most exciting collection of targets. 7 rocky, Earth-sized planets orbit a small red star, 3 of them in the habitable zone. Outer habitable zone planets like D, E, F, and G are ongoing targets with better prospects for having retained atmospheres worth characterizing. Every observation cycle brings new data. JWST cannot directly image a true Earth-sized planet orbiting a Sun-like star. The contrast is 10 billion to 1, like spotting a firefly next to a floodlight from across a city. This is why the Habitable Worlds Observatory is the top priority flagship mission. It will use a coronagraph to block the blinding light of a star to reveal nearby planets. The mission is designed to directly image around 25 Earth-like planets, searching for oxygen, ozone, water, carbon dioxide, and methane simultaneously. Launch is planned for the late 2030s. On the ground, a new class of extremely large telescopes is under construction. The ELT in Chile, scheduled for 2028, will be capable of high-resolution atmospheric characterization. The Giant Magellan Telescope and the Life mission concept, using multiple spacecraft flying in formation, will provide independent routes to biosignature detection. And then there is SETI. For decades, scientists have been listening to the radio sky for signals that could only mean another technological civilization had built a transmitter. Frank Drake formulated the equation that bears his name, a mathematical framework for estimating communicating civilizations. It is a tool for organizing our ignorance. Today, the most ambitious SETI effort is Breakthrough. Listen, surveying thousands of stars, no confirmed signal of extraterrestrial origin has been detected. The Fermi paradox remains as sharp as ever. If civilizations are not rare, the galaxy should be full of detectable signs. The fact we see none is a profound clue. So where does all of this leave us? We have confirmed that the basic chemistry of life forms spontaneously across the cosmos, and that liquid water oceans are common. We are beginning to read the atmospheric chemistry of planets orbiting other stars. While we have not yet found a definitive biosignature, we have barely begun this search. The answer matters profoundly. If we find life, it would transform our understanding of biology from the study of one example to a genuine science with multiple data points. It would tell us that life is a natural consequence of chemistry. If we find nothing, it suggests a near impossible hurdle separates chemistry from living organisms. Either way, we are the first generation who actually have the tools to find out. That is perhaps the most consequential privilege any generation has ever had.